Hello everybody, and welcome back. In this quiz tutorial, we're going to be covering quiz number 33, which discusses the Rayleigh-Ritz method specifically for Euler-Bernoulli beams. So as you guys remember from the last quiz, we've already discussed what the Rayleigh-Ritz method is and how we can use it to approximate solutions. This quiz is basically the exact same, just a continuation, more specifically to Euler-Bernoulli beams. So of course, Euler-Bernoulli beams, those are one of the most common things that you guys will encounter in structural engineering. So we're going to figure out, all right, how can I approximate a solution for these Euler-Bernoulli beams? Now, before we begin into the theory, I just want to say thank you to all of you. This is the very last quiz, and I can't believe it. It's went by really fast. I've had a lot of fun doing these for you guys. I'm really happy how much you guys have liked these quiz videos. Anything I can do to help you guys let me know, and I'll make sure that I do it for you. So again, thank you guys so much. I really appreciate all the support that you guys have given me. And again, if you guys need anything, you let me know and I will make sure it happens. All right, guys, let's jump into the theory. So again, this quiz is basically just a continuation of last quiz, quiz number 32, where we talk about the Rayleigh-Ritz method, which is based on potential energy. So as we said, in the Rayleigh-Ritz method, in order to find the coefficients of our approximate solutions, we use the concept of potential energy to figure out what those coefficients are. And in this quiz, we're going to look at the potential energy specifically for beams. So remember that the potential energy comes from two different things. The first one is the total strain energy, and the second one is the work done on the system by the external forces. And we said in this course, we dealt with two different types of beam scenarios. The first one is a beam under axial loading, where the total strain energy is simply EA divided by 2, multiplied by the derivative of the displacement function squared, and all of that is then integrated over the length of the beam. So again, that's the total strain energy. And the work done on the system, of course, is our laterally distributed load times the displacement integrated over the length of the beam, minus the summation of any concentrated forces multiplied by their corresponding displacements. Now, again, that's a beam under axial loads, but as you'll see in this specific quiz, we're going to talk about the Euler-Bernoulli beam, and the potential energy is simply, again, the total strain energy minus the work done on the system by the external loads. But in this case, as we can see, our total strain energy equation changes a little bit, where it's equal to EI divided by 2 multiplied by the second derivative of our displacement function squared and then integrated over the length of the beam. Now, we also have to include the fact that there's also work done on the system by external loads, which in this case is the integral over the beam of any distributed loads Q multiplied by the displacement Y, minus any concentrated loads multiplied by their corresponding displacements, and then minus any concentrated moments multiplied by their corresponding rotation. So as we can see from this, if I am interested in the potential energy, I can calculate the total strain energy, I can calculate the work done on the system, and then all I have to do is go the total strain energy minus that work done on the system. And as you guys are going to see in this quiz, we're going to focus on how can we determine that total strain energy and how can I determine the work done on the system. So that's basically it for the theory, guys. Let's jump into the quiz. Alrighty, guys, welcome to the quiz. As you guys are going to see, the quiz is 3 questions long, but it's actually 2 questions long. And the reason why is because in your guys' quiz on E-Class, questions 1 and 2, it's basically the exact same question. It just wants different things with the beam. So we're going to discuss what that is. And then question number 3 is my question number 2. So don't worry, in the end, I'm going to cover absolutely everything you guys have on your E-Class quiz. It might just not be the same numbering as you guys are used to in E-Class. All right, so if we look at question number 1, it says, an approximate solution using the Rayleigh-Ritz method is sought for the shown beam. So we have a nice shown beam down below, and it says the beam has a Young's modulus E and moment of inertia I. As the first step in the method, a second-order polynomial displacement function satisfying the essential boundary conditions is obtained as y is equal to a2 x1 multiplied by x1 minus L. And it wants us to determine 2 different things. In part A, it says the total internal strain energy of the beam, and in part B, it says the work done W by the external forces on the beam. And this is why things differ a little bit than E-Class, because in E-Class, part A here, this is your E-Class question 1, and then part B here, this is your E-Class question number 2. So this is what I mean, where the numbering is going to be a little bit different, but in the end, I'm going to cover everything you guys need to know. All right, so I'm going to scroll down here a little bit because we don't really need that information because I have everything that we need right here. We have our beam, we have our loading scenario, and we have our approximate solution right here. So as we can see here, our current approximate deflection is y is equal to a2x1 multiplied by x1 minus L. And of course, the main goal of the Rayleigh-Ritz method is to figure out what exactly that a2 is. Now in this particular quiz, it doesn't ask us to solve for it, so we're not going to, but as you guys will see, this is the goal of the Rayleigh-Ritz method as a whole. So I want to make sure you guys are aware of that. All right. So what we're going to do is we're going to start off with question 1, or I guess part A, and it wants the total strain energy. So I'm going to put this as TSE, and this is how I define total strain energy because, well, I'm lazy. I don't really want to write out total strain energy if I'm being honest. And we know that for an Euler-Bernoulli beam, this is going to be the integral over the length of the beam. So I'm going to integrate from 0 to L of EI. So this is that flexural rigidity term. And this is going to be divided by 2 and then multiplied by the second derivative, so d squared, of our deflection term, so d squared of y with respect, of course, to x1, and this is squared. And then the whole term here is squared, and that's very important. Don't forget that that whole derivative term is squared after you obtain it. As you guys will see, that'll lead to a bit of a trick. So what I'm going to do is we're differentiating with respect to x1. So this is our formula right here. So the question really becomes, do I have everything I need to solve for? Well, EI divided by 2, I know what those are. Those aren't going to be a problem. The next term, the second derivative, well, I actually don't know what that is yet, but I can solve for it. So I'm going to switch my pen here, and let's go to pink, and I'm just going to scroll down a little bit, because we know from above that y is actually equal to a2 times x1, all multiplied by x1 minus L. I said x1 minus L or L minus x1. No, x1 minus L, so I'm good so far. Now what I'm going to do, because I'm really bad at taking derivatives, is I'm just going to expand this out. So I'm going to have a2 times x1 squared minus a2 times x1 times L. And again, I'm just doing this because I'm absolutely terrible at taking derivatives. It's easier for me to expand it out into single terms rather than have that x1 minus L as kind of a factor there. All right, so now that I have this, I can take the second derivative pretty easy. So d squared of y with respect to x1 is going to be equal to, so I'm just going to put the square equal to, and I'm just going to go through each of the terms. So if I look at this first term right here, a2 x1 squared, well, I know if I take the derivative of that once, I get 2a2 times x1. Take the derivative of that bad boy one more time, I simply get 2 times a2. So that's from the first term there. And I say, all right, well, I have to keep in mind I got a second term here. So if I look at that second term, I take the derivative once, I get a2L. Take the derivative yet again, there's no more x's, so therefore this is actually minus 0. Because if I take the derivative of that last term twice, I get 0. So therefore my derivative term is actually just equal to 2 multiplied by a2. Nice and simple. And I say, all right, Clayton, this is great, because now we can substitute everything into our integral and solve. So I'm going to scroll down a little bit right now and say, all right, well, we remember that TSE over here is equal to that integral, but now we say that, oh, hold on one second, this EI term that's present here, that's actually constant. So since it's constant, we can pull it outside of the integral. So I'm going to have EI divided by 2, and then I'm going to integrate whatever's left in there. So I'm going to go the integral from 0 to L, because I'm going all the way across that beam, and we have our derivative, which we know is simply just going to be 2a2. And remember, this is squared. If you guys don't forget that squared, you guys will get the wrong answer. And from what I've seen on previous final exams, that's what will get most students. I guarantee that in a multiple choice exam, they will have the option, if you forget, to include that squared. I guarantee that they're going to have it. All right. So what happens is we say, all right, well, this integral is not looking too bad. So this is actually equal to EI all divided by 2. And then we have our integral. So we solve the integral. We know that if we integrate 2 times a2 squared is simply 4 times a2 squared, we just get that it's equal to, I say it's simple, but yet I mess up right away. We're going to get 4 times a2 squared. So this is just factoring in that squared. And then we have x1. And we know that we're integrating this from 0 all the way to L. So therefore, it's pretty simple that simple to see that our answer is going to be 4a2 squared times L, and then all multiplied by that constant out in front, which is EI, all divided by 2, and that's it. So all we need to do to find out our answer is just simplify it. So I'm going to come down here and say, all right, well, our total strain energy, my TSE, it's equal to, I see I got a 4 at the top, I got a 2 at the bottom. Therefore, this will simplify into 2. A2 squared, well, that just stays A2 squared. L is just L, so I'm going to have L. And then at the end, I have an EI. So there is my answer right there, ladies and gentlemen. So hopefully that wasn't too bad for you guys. If I can do the integral, then you guys can do the integral. I am absolutely terrible at integrating as well as derivatives. You guys are experts. You guys are probably laughing at how long that took me. All right, guys. That's question 1 or / part A, which has to deal with the total internal strain energy. So that's, again, question 1. But if we look at question number 2, it says, what is the work W done by the external forces on the beam? So I'm actually going to start down below here real quick, because what we're going to do to start this question is we're going to write the formula. So I'm going to go part B, and we know that the work done is actually equal to a couple things. The first one is the integral of the distributed load Q multiplied by the deflection y, of course with respect to x1, plus the summation of any concentrated forces that we have multiplied by their corresponding deflection, and plus the summation of any concentrated moments that we have multiplied by their corresponding rotations. Now, I wrote the summations very sloppily, of course. Of course, we need to consider I is equal to 1 over n, all that crap, but I'm just doing this nice and simply because what we're going to do is we're going to look at our current loading scenario. So I'm going to switch my pen here, and I'm going to look up at the beam. Now, if we look at this beam, the only external loads that we have on this sucker is that distributed load Q. There is no concentrated forces, and there is no concentrated moments. Now, someone might try and argue with me and say, hey, Clayton, what about this? We have a reaction force over here. Isn't that a concentrated load? And I would say, you know what? You're right. That's exactly what it is. That would be a concentrated load. But if we actually come down here, we see that if we ever have a concentrated load F, we multiply it by its corresponding deflection. Now, if we look back up at the beam and we see that this concentrated load is due to a support, well, of course, we know that the deflection at the support is equal to 0. So even though we do have a concentrated load at the supports, once we multiply them by their deflections, which is 0, it actually effectively becomes 0. We don't need to worry about that. So I'm going to erase that. We don't need to worry about that. So if we're looking at this beam, the only thing that we do have to consider in our calculations is going to be this distributed load Q, which of course is great because I can come down here to my nice equation and I say, well, is there any concentrated moments? Well, no, there's not. So we can say, all right, I don't care about that. Is there any concentrated forces that don't have a displacement of 0? Well, the answer is no. I don't have to worry about that either. Therefore, my work done on this system is simply just the integral of our distributed load multiplied by the deflection. Now, here's the trick though. If we come up and look at our beam once again, and I'm probably giving you guys motion sickness going up and down, we have to realize that our distributed load Q isn't over the entirety of the beam. It starts off over here at x1 is equal to L over 2, and it ends over here at x1 is equal to L. So therefore, when I'm integrating this, I don't integrate over the entirety of the beam. I'm just integrating where that distributed load is. All right. So what I can do is I can come down here and say, all right, since that's my function, well, I can simplify it a little bit where I know that my work done is equal to the integral wherever that distributed load is. So we know that this is from L over 2 all the way to L of Q. Well, Q is just Q, so we don't have to worry about that too much. Multiplied by our deflection, which we said is equal to A2 x1 squared minus A2 times x1 times L. And of course, this will all be with respect to dx1. So all we have to do is actually just solve this integral. And as you guys are going to see, it's not too bad. The first thing that we can see is, all right, well, Q is a nice constant. So therefore, I can move that bad boy out. I don't have to worry about that at all. And all I have to do is integrate everything that's inside. So what I'm going to do is I'll switch colors to show you guys. Again, I'm not the best at integrating. So if I can do this, you guys can too. If we're looking at our first term here, we see that we have A2. So I'll go A2 we have x1 squared. So we know that once we integrate x1 squared, it's going to go up a power. So this will be x1 cubed. And then we have to pull down that 3. So we're going to have a2 over 3 effectively. I'll switch colors again. And green. Yeah, why not green? We're going to look at our second term here. So we go minus, we have a2, that's just a constant. We have L, that's just a constant. And then we have an x1. Now we know that once we integrate x1, this will become x1 squared. And we're going to have to pull that 2 down over here. All right, so hopefully that wasn't too bad for you guys. It's usually pretty bad for me, so that's why I'm hoping you guys don't suffer the same fate that I typically have. Now, the key thing to keep in mind here is our integration limits. We know that we're integrating from L over 2 all the way to L. It's not from 0 to L, it's from L over 2 all the way to L. So all we're going to have to do is substitute all of that in. I say, all right, well, I have Q out in front. That doesn't change. It's my nice constant. And then I get A2 divided by 3 multiplied by x1 squared. So once I substitute L in there, x1 cubed becomes L cubed. So this will simply just be L cubed. And I say, all right, well, in my next term, I have minus A2 divided by 2 multiplied by L, and then multiplied by x1 squared. So, of course, when I substitute x1 is equal to L, I get L squared. Something like that, not too bad. Now, normally this is where our integration ends because we go from 0 to L, but now we must also consider this part right here where we're saying, all right, well, we also have to consider the L over 2 terms. So we go minus, and then we got A2 over 3. So again, this doesn't change. A3 over, nope. A2, don't be an idiot, Clayton. Last quiz, try and stay strong for a little bit longer. And then we have x1 cubed. But now when we substitute our value, we're substituting L over 2 instead of L. So what happens in this case is we have L cubed all divided by 2 cubed, which we know is actually 8. And say, all right, well, then I go minus, but then we go minus minus, so this is actually a plus. We have A2 over 2, so A2 all divided by 2, and then we have L, so L doesn't change, and then we substitute x1 is equal to L over 2 into the x1 squared. We got L squared all divided by 4, and I'm running out of room. I'm really sorry, guys. I'm not the best at space management. All right, so let's try and wrap this up right here so we can start a new line and look a little bit better. So if there's one thing that I'm noticing, and let's switch my highlighter, I see that in each one of these terms, I have an A2, so A2, 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 as well as A2. And then I also see that I actually have an L cubed. So I got an L cubed there. L multiplied by L squared, that's going to be L cubed. Right here I got L cubed. And then L multiplied by L squared, another L cubed. So what I'm going to do is I'm going to factor out all of those constants. So I have Q multiplied by A2 multiplied by L cubed. And then it's basically just a bunch of factors inside. So if we look at the first one, after I factor out A2L cubed, what you guys will see is you get 1/3. Moving on to the next term, factor out the A2L cubed, I get subtract 1/2. And then go on to the next term, etc., etc. So the next term, negative 1 over 24. And our final term, we actually have 1 over 8 after we factor everything out, which is great because all I'm going to do is take all those numbers, throw them in my calculator and see what they simplify to. And in the end, you guys will get Q times A2 times L cubed. So again, these are just my constants from above. And what we find is that actual simplification of all those numbers is negative 1 over 12. So we actually put a negative sign here, and all of this is actually going to be divided by 12. Therefore, my work done on the system by the external loads is going to be negative Q times A2 times L cubed, all divided by 12. So as you guys are going to see, not too bad of a question, and we're going to just highlight this right here. Just like that. Perfect. So that's actually question number 2, or part B. And as you guys have seen, even though we talk about potential energy, we don't actually calculate any of the potential energy. So all I'm going to do right here, and this is purely extra, so don't worry about this if you guys just want to focus on the quiz. This is purely extra. I'm just going to show you guys what we do with the Rayleigh-Ritz method really quick. We say, all right, our potential energy is equal to our total strain energy minus the work done on the system. So all we have to do is take our total strain energy, which we found as 2A2 squared L times EI. So I'm going to come down here and say, all right, this is 2 multiplied by A2 squared multiplied by L multiplied by EI. And we minus the work done on the system, which we have as negative 12. So this is going to come to a positive, plus Q multiplied by A2 times L cubed, all divided by 12. So just like this. And what we do next is we actually say, all right, we know that we want our potential energy to be a minimum. Therefore, what we're going to do is we take the derivative of the partial energy, or potential energy, not partial energy, with respect to our constant. In this case, it's actually equal to A2. Therefore, if we look at top here, I'll switch to pink, we have an A2 squared on one term, and then we simply just have an A2 over on the other term. So this will become 4A2 multiplied by L multiplied by EI plus, we can see that that A2 is the only A2, therefore it's just going to go away. Q multiplied by L cubed, all divided by 12. And again, what we know is we want this to be minimum, so therefore this derivative is going to be equal to 0. And if we look at this equation, we have one equation with only one unknown, which is A2. So this is why we use the Rayleigh-Ritz method, because after we find that potential energy, we take the derivative of it, make it equal to 0. Therefore, in this case, I can solve for my value of A2. Again, this isn't asked for in the quiz, but if you guys want to know why we're solving for the total strain energy and the work done on the system, this is exactly why we're doing it. All right, so hopefully that answered some of your guys' questions. We'll jump on over to question number 3, which is right here. And question number 3, again, this is 3 on E-class, but I labeled it as question number 2 because, I don't know, maybe I just like to trick you guys a little bit. All right, so question number 2, or 3, says, an approximate solution using the Rayleigh-Ritz method is sought for the shown beam. As a first step in the method, a fourth-order polynomial displacement function satisfying the essential boundary conditions is obtained. The following is a candidate function that satisfies the essential boundary conditions. So what we're basically given is 4 functions, and the question just wants us to say, yes, this satisfies the essential boundary conditions, or no, it does not. So there's only one equation here that actually satisfies all of those essential boundary conditions, and it's our job to figure out what exactly it is. So what I'm going to do is I'm going to switch over to green because we need to talk about those essential boundary conditions. So remember, essential boundary conditions only are boundary conditions for 2 things, displacement and rotation. That's it. So if we were to look at this beam here, on the left-hand side, we see that it is fixed. Therefore, we know that y at 0, the displacement, well, that's going to be equal to 0 because it's fixed. We also know that since it's fixed, the rotation at y is equal to 0 is also equal to 0. So again, that's because we have a fixed end. The displacement and the rotation there is equal to 0. If we look at the other side and we see that we have a roller support, we know that, of course, the displacement at x is equal to L is going to be equal to 0. And that's because of that roller support. So if we look at this loading scenario, we have 3 essential boundary conditions that must be met for our approximation equation. So all we're going to do is look at these 4 approximation equations, and if they violate the essential boundary conditions, we know that they are wrong. All right? So what I'm going to do is I'm going to scroll down, and we're going to look at A, where we have y is equal to a4 multiplied by x1 to the 4th. And this is probably the most obvious. It does not satisfy, because if I were to look at the value y is equal to L, which we know must be equal to 0, if I were to substitute that into the equation, I get a to the 4, L to the 4, and of course this does not equal 0. Therefore, I know that A is not the correct answer at all. All right, so the next one that's very obvious, does not obey, is equation D. And the reason why is because if we look at y at 0, what we get is this is actually equal to a to the 4. And then inside the brackets, we have L minus x1. So L minus 0, well, that's just going to be L. And this, of course, will be to the 4. And if we know from their fixed end that this must be equal to 0. And since this is not equal to 0, we also know that D does not equal to 0. So the remaining ones that we have are equation B and equation C. And as you guys will see, when it comes to y at 0 is equal to 0 and y at L is equal to 0, both of these equations satisfy those ones. So there's only one more essential boundary condition that we have, and I'll change my highlighter, which is this one. We know that the rotation at x1 is equal to 0 must be 0. The problem with this, we actually have to take the derivative of these functions to figure out what that rotation is. All right, so this is a little bit tricky because I'm terrible at derivatives, but let's look at equation C. So I'm just going to keep equation C up at the top. I'm going to say, all right, well, we got y prime is equal to, and since we have two different terms that are a function of x1, we have to do the product rule. And I know product rule, Clayton, that sucks ass. I don't want product rule. I agree. I don't like it either. But luckily for you guys can just throw it into Mathematica. All right, so the product rule states that we take the derivative of one and then we add it to the derivative of the other. And I know that doesn't make any sense, but it's basically this. I look at my function and I look at the first term that has x1, which is right there. What I'm going to do is I'm going to take the derivative of that. So I get a4. I take the derivative of x1. Well, of course, that's just going to be 1. And then the other term that has x1, I just leave the same. So I'm going to go L minus x1 cubed. All right, so that's the first one. And then I add this to the same process, but now I take the derivative of the other term. So a4 in this case, multiplied by x1, that stays the exact same. I just take the derivative of L minus x1 cubed. All right, so I know that when I take the derivative there, I'm going to take that exponent down to the bottom. So I'm going to have 3 of L minus x1. Since I took the derivative, that 3 now becomes a 2. And then, of course, we have to take the derivative of that. Well, I was going to say the baby. So this is what people called it in high school, this little part right here. They called it the baby. Don't ask me why. I have no idea. But just remember that once we take the derivative of something like that, we have to take the derivative of the baby on the inside here, which is simply -1. All right, so it's a lot of work, but as you guys will see, this simplifies into a4 multiplied by L minus x1 cubed minus a4 times x1, I guess multiplied by 3, multiplied by L minus x1. So it's a bit intuitive where you actually need to do quite a bit of work. But now remember, the goal here is making sure that this equation satisfies the essential boundary conditions. So we know that y prime at 0 in this case, so y prime at 0, all we have to do is substitute x1 is equal to 0. What we see is that we get a4 times L cubed minus 0. So this is actually equal to a4 times L cubed. This does not equal to 0. So therefore, we know that equation C over here, this one also does not satisfy the essential boundary conditions. And what you guys will see once you guys take the derivative of equation B, it will satisfy that rotation boundary condition. Therefore, we know that B is going to be our answer. All right, guys, so that's it for the quiz. Very last quiz. I really can't believe it. I cannot thank you guys enough. I'm so proud of absolutely every single one of you. You guys have done amazing this term and have made my life just so much more easy as well as fun being a TA. You guys have asked great questions. You guys have helped me learn to be a better instructor. So I cannot thank you guys enough for all that you guys have done. So again, thank you guys so much. Typically at this point, I say I'll see you guys in the next quiz, but since there is no next quiz, I'm at a little bit of a loss for words right now, guys. Almost a little emotional, if I'm being honest. So I guess I'll say thank you guys so much for watching. I will see you guys in the final exam.